So in this video lesson, we're going to do a very brief explanation to a really simple stoichiometry problem of the type that you would do following a titration lab. Okay, so this is the kind of math that we do when we're doing titration. We're using two solutions, one of which whose concentration is known, to find the concentration of the solution whose concentration we don't know. And these two solutions have to react together in some measurable way, so you know when there's what's called an end point. A neutralization point in the case of acids and bases is an end point. Okay? And so it is stoichiometry, so we have to have a balanced equation. So we know we have HCl as one of our chemicals. We have NaOH, it's another of our chemicals. And so you need to figure out whether these things, well, they are solutions, and it doesn't say what the solvent is, so it's assumed to be water. Anytime you're told you have a solution and the solvent isn't named, then the expectation, the implication is that it's aqueous. If there is any other solvent other than water, you have to state what that solvent is. So both these are aqueous. And then we have to figure out, well, what kind of equation it is. Okay, so that we had a unit where we learned how to classify equations. This is a double replacement reaction. I've got two-part chemicals. This is an acid, and I've got a hydrogen and chloride. This is a base. I've got a hydroxide on the back. It's got hydroxide as a polyatomic ion, indicating that it's an ionic compound. So when you react an acid with an ionic compound, you're going to get a double replacement reaction. Hydrogen's going to join up with the OH on the back, the hydroxide on the back, and we get HOH. Sodium's going to join up with the chlorine, and what that means is we have basically table salt. Okay? So we need to know the physical states now. So we're going to look up on the solubility rules and find that sodium compounds are always soluble. If you look up chloride, you find that it's also soluble with a couple of exceptions, but not when it's bonded with sodium. So this is aqueous. And then this is water. You need to recognize water when you see it. Know that unless there's heat involved, as with a combustion reaction, water is going to be a liquid. Okay? And so we've got an equation here that's not yet balanced, or it might be balanced, we haven't checked it. So we want to use what's called an atom inventory to check it. So we're going to list all of our elements on the left side, H, and then Cl, and then Na, and O. Hydrogen, chlorine, sodium, and oxygen. We're going to make a kind of a grid here in which to do this atom inventory. And we're going to count all the atoms on the left. And I've got one hydrogen here and one here. That's 2. 1 chlorine, 1 sodium, and 1 oxygen. On the other side, I've got 2 hydrogens, 1 chlorine, 1 sodium, and 1 oxygen. So that's already balanced. Now, a lot of times it will be balanced, but sometimes it won't, and you need to make sure that it's balanced before you move forward, because stoichiometry doesn't work unless you have a balanced equation. So we're going to choose to start with the chemical whose concentration we know. Okay, and then we're going to calculate our way to the amount or volume of the other solution. So we're going to start with this 0.50 molar HCl solution, but I've got to break that into the component measurements that make up molar concentration. M underlined means molar concentration. The component measurements that make up molar concentration are moles of solute and liters of solution. So we're going to take 0.500 moles of the solute, that's HCl, in 1 liter of HCl solution. Now, when I told you how to calculate molarity of solutions, I said you need to make sure that you specify what the solvent is in the solution. the solute is in the solution. When you're writing these broken out or split out units of measurement that make up molarity, and this is why. You're going to see why it comes. Hopefully you'll be able to see why now. Okay. All right. So what I need to do is to find out how many moles are in this, because in order to use stoichiometry, you've got to get your starting amount into moles. Okay. Well, the only way to do that is to take the volume we started with and use that to get rid of the volume. Okay. In order to get the moles. Well, we get rid of that by putting 56.35 milliliters of that HCl solution on the top over 1. Okay, that's an amount. We're going to put it over 1. Now we need the conversion that's going to get rid of both milliliters and liters. And the relationship, the mathematical relationship between liters and milliliters is there are 1,000 milliliters in 1 liter. Okay, now for me, it's required that you write out those equality statements before you write the conversion unit. Okay, so you're going to justify this conversion unit by writing this out. So we want to put 1,000 milliliters in the bottom here because that allows you to cancel milliliters there. Milliliters on the top, milliliters on the bottom cancel out, and the 1 liter goes in the top. That cancels out the liters down here. And so we can cancel out milliliters, we can cancel out liters, we can cancel out HCl solution, and we are at moles. And that's where we want to try to get to start. All right, now that we've got the starting amount into just moles, we can use a molar ratio to go to the other chemical we're interested in here, which in this case is the NaOH solution. That's this stuff right here. So we need a molar ratio, and we're going to put moles of HCl from the balanced equation on the bottom. Since the coefficient here is an implied 1, we're going to put 1 mole of HCl on the bottom. That'll allow me to cancel moles of HCl because I got 1 on the top, 1 on the bottom. And I'm going to put the 1 mole of the other chemical we're interested in on the top because I have an implied 1 there. Now, if there were any other number there, you'd have to use that number here instead of the 1. You can't just put 1 there. You've got to use whatever coefficients there are in the balanced equation. If there are no coefficients, it's implied to be 1. All right, so now we've canceled out, well, we were able to cancel out moles in HCl, and we're at moles of NaOH. Okay? All right, now, molar concentration is moles of solute over liters of solution. So we need to get liters of this NaOH solution on the bottom. So we don't have it in liters yet, but we do have the milliliters of that NaOH solution. So I'm going to put that on the bottom. Now that we've got milliliters in the bottom, at the moment we have moles of solute over milliliters of solution, but we need to have liters of solution. Well, there's an easy conversion. It gets to liters. Okay, so we'll put 1,000 milliliters on the top. It's off the screen there, isn't it? Over 1 liter. That's going to cancel the milliliters, and we have moles of solute over liters of that same solution. So notice we have 2 different solutions here, and the reason I want you to say that it's a NaOH solution or an HCl solution is because you've got 2 different solutions. In order to keep them straight, you need to write out which kind of solution it is. That's why I want you to do that. So we have everything we need now to calculate the concentration of this NaOH solution. We've got moles of solute over liters of solution. We're ready to calculate. So this is the number I get from my calculator, and we have moles of NaOH on the top, and we have liters of NaOH solution left on the bottom. We're going to round it off, and I've got 3 significant digits in this measured number, 4 significant digits in that measured number, 4 significant digits in that measured number. So this is the number with the least digits, 3. Leading zeros are not significant. Trailing zeros are significant. If it's a decimal place, 1, 2, 3 significant digits. So we want our final answer to have the same number of significant digits. Again, leading zeros are not significant. 1, 2, 3 significant digits. All others are insignificant. And so our answer is going to be 0.41. This 7 being rounded off makes that 1 a 2. And moles of NaOH over liters of NaOH solution is molar concentration of the NaOH solution. Okay? And so using this titration process in the lab and then doing this kind of calculation, using the amount of acid we use to titrate, we can find the concentration of the sodium hydroxide solution. Any questions? Yes? Okay. There's a problem for you to practice now. You may work with a neighbor. In fact, I highly encourage you to work with a neighbor, especially before you call on me to come help you. I've given you the process. Now you just got to follow that process. All right? So when we set up the problem, here's what we know. The solution whose concentration we know is what we start with. We multiply by the volume of that solution and then convert that solution from milliliters to liters because we need it in liters. We need to convert the liters in order to get rid of the liters here and leave ourselves just with the moles. Then we put the molar ratio in here to get to the other species, the HI species. Divide by the volume and then convert that volume to liters here, and we get this answer in the calculator, 0.1942595997806 moles of HI is what I have on the top. Liters on the bottom of HI solution is what I have. And so we need to get our significant digits right. I've got 3 significant digits here. The leading zeros are not significant of the measured and calculated numbers, and those are the ones we use for figuring out significant digits when we're doing multiplication and division. This one has 3, this one has 4, this one has 4. We want the final answer to have the same number of digits as the measured or calculated number with the least digits. Leading zeros are not significant. 1, 2, 3 significant digits. Underline everything else. Draw an arrow. That's the only operator that's allowed to show you rounding off. We have 0.194 moles of solute over liters of solution is molar concentration, so we can symbolize that as a capital M with a line under it, and just say that's the, I'm sorry, not N, but HI solution.